We're looking at integration techniques, and in this particular section we're looking at partial fraction decompositions. Now, partial fraction decomposition process is really nice for rational expressions. It doesn't work with anything to do with a radical. So again, it's good for rational expressions. Now, if you recall, a rational expression is something with a numerator over a denominator. So a numerator over a denominator. But the numerator and denominator cannot have any radicals or exponentials. So nothing with a square root, nothing with an e to the x or something like that. And natural log, of course, would come in here too, or any other log. So that's what partial fractions work really well with. So when I talk about a numerator over denominator, we're talking about a polynomial. Now, when we're working with a partial fraction decomposition, I always need to make sure before I get started that the degree in the numerator is less than the degree in the denominator. If this isn't true, I have to do long polynomial division. So long polynomial division is an algebraic technique that you may or may not remember from algebra. We probably looked at synthetic division as well as long polynomial division at the same time. But we would do long polynomial division, and then we would go ahead and do the partial fraction decomposition about the remaining expression. So this is an important topic. The degree in the numerator has to be less than the degree in the denominator for our polynomial expression. Now, if you try this method and the degree in the numerator is greater than or equal to the degree in the denominator, everything will work great. But you'll get the wrong answer in the end because it has to be in this particular form before we can get started. We're going to have to use a lot of algebraic techniques here. It's solving. We could use systems of equations to solve. We could also use some linear algebra, but we'll probably stick with substitution and systems of equations. Now, when we're talking about partial fraction decomposition, we have to remember that this is an algebraic technique. So we're going to be doing a lot of algebra. Most of our work here will be algebra in the setup. But once we get done with the algebraic technique, we're going to have to integrate the resultant expression. And a lot of times one of the integrals that we'll be working with is the integral of 1 over u du. So as a quick review, this is natural log absolute value of u. A lot of times we'll be stuck with some trig sub. So trig sub could come up as well, which we learned in a previous section. And a lot of times we could just recognize a few forms too. So some of the forms that we look at from a previous section with trig integrals was 1 over a squared plus u squared du, was 1 over a inverse tangent u over a plus c. So this will come up a lot as well. Be careful when you're working with a partial fraction decomposition. There's a lot to keep track of, and these are really long problems, so make sure you don't drop any of your work. Let's go ahead and look at the steps of the procedure. So the first thing that we'll do is we'll go ahead and fix any top-heavy fractions. Now, when we talk about top-heavy fractions, that means basically that the degree in the numerator is greater than or equal to the degree in the denominator, and we fix this by long polynomial division. I like long polynomial division, but I don't know if we'll get to do a problem with one of these today or not because they do take quite a while. And then once we got to long polynomial division, we would be at our second step. Second step would be to factor the denominator completely. If it's not in complete factored form, our process won't work. Or it will work, but it'll work incorrectly. So factor the denominator completely. Now we're going to end up with linear terms and irreducible quadratic terms. So linear and quadratic terms. Now when we take these linear and quadratic terms that we have in the denominator, what we'll do then is we'll decompose the fraction. And I'll show you an example of this. Instead of just using variables, we'll put numbers to it and it'll make a lot more sense. So we'll decompose the fraction. Now when we talk about decomposing the fraction, we have linear terms and then we have the quadratic terms. So let's go ahead and talk about the linear terms first. So for my linear terms, these would be terms like ax plus b. mx plus b would be a line, so these would be like ax plus b is what we use for the generic. What I look at is that each of the numerators is one less power than the denominator. Now we're only talking about the base, so we could have a base of, let's say, ax plus b. And then I could also have, let's say, something like ax plus b quantity squared. This is still linear. The base is linear. This is what's important to me here, is that the base is linear. I could have ax plus b cubed, and you can see that this process could expand. Now, the coefficient in the numerator, I should be careful here. I'm going to make these lowercase a's. And the reason I'm going to make them lowercase a's is up above we'll use uppercase just to distinguish. 1 degree less than a line is a constant. So if we talk about taking the derivative of ax, I would get a, which is a constant. So each of these would be a constant in the numerator. And these would go all the way up to whatever letter or how many factors that we have. I certainly wouldn't want to work a problem with this many factors. So this would be ax plus b to the n. We could technically call it 26 because we know there's 26 letters in the alphabet. So each linear term combines n terms to this expression, and this will make more sense when we look at an exact problem. Now we also have quadratic terms, and that's the highest power that we're going to go with, is the highest irreducible quadratic. So if with the quadratic, quadratics look something like ax squared plus bx plus c, if you'll recall. And of course these could be to the nth power, so I could have several of these terms. Well, if this is the case, my ax squared plus bx plus c, what I would do then is I would go one less power, just like I did at the top. So when I had a linear, I went one less to a constant, and then when I had a quadratic, I'm going to go one less, and one less power than a second degree polynomial would be a first degree polynomial. So this would mean ax plus b. And it's important that we distinguish between the lower and the upper case here, otherwise it gets a little bit confusing. So ax plus b, cx plus d, ex plus f, and you can see that this process would continue on in a similar fashion. So these can get out of hand pretty quick if we end up with lots of quadratics, and so we'll have to be really careful about keeping track of every single term every single time, so it'll be really important. Now, we haven't put any numbers to anything yet, but we do have a couple more rules that we need to look at. There's a point here that we need to check our work. Now, if we look at the degree of the denominator, the highest degree of the denominator, all the combined powers, that better equal the number of A, B, C's, and D's that you get in the numerator. So this is the number of A, B, C, D that you get. So this is a quick spot to check. If this isn't happening, that tells you that you may want to double check everything. Now, don't expand anything. There's no reason to take ax plus b and actually square it, or ax plus b cubed and actually square it. We want to leave things in factored form because they're easier to integrate in factored form. Now once we get this process done, what we're going to do is we're going to solve for all these variables. So we're going to solve for a, b, c, d, etc. There's a couple different ways we can do this. We can do it by substitution. And the reason we like substitution, it leads to elimination, of course, of a variable. And we can also look at this by equating coefficients. So there's several different ways that we can do this. Now when I'm working through some of these problems, it will depend on the problem that we're looking at. So some problems are a little bit easier to work with equating coefficients, and some are easier to work with substitution or elimination. But we'll look at each individually. So to recap, let's run ahead and run up here again. Partial fractions are really good for expressions that have a numerator and a denominator, polynomials, meaning algebraic expressions with no radicals, exponentials, or logs. So we're looking at fractions here with no radicals, exponentials, or logs. For our first example, let's consider the integral. Let's do 5 over x squared plus x minus 6 dx. Now, we could try to integrate this as is. We could say, oh, let's let u equal x squared plus x minus 6. and then du would be 2x plus 1 dx, and you can see we don't have anything that could get us to a 2x plus 1. It's just not there. So this doesn't work. I don't have what I need to get for my du here. I could try to complete the square. That might be an option here. If I look at this in terms of completing the square, I'd take half this linear term and I'd square it, and you can see things get out of hand pretty fast right here when I try to complete the square. So I think I could solve this by completing the square. And then once I complete the square, I would use a trig sub or a trig integral. And I think this one would probably fit the form of a u squared minus a squared. And so if you remember from previous lectures, then I would make a substitution of u equal a secant theta. So trig sub or trig integral might fit a form as well. Okay, so that could be one way I could work with this. Of course, I want to focus in on partial fraction decomposition because sometimes these don't have options of other techniques. So when I look at this expression, I wonder where it came from, meaning I had two fractions at one time that I added together to get 5 over x squared plus x minus 6, and I'll write that a little different. So, what two fractions did this come from? What two fractions did I combine? Well, the only way we can really figure out what that is if we factor this. So let's go ahead and do back one more step. This would be x plus 3 times x minus 2. So that gives us an idea. It came from two fractions, one with the denominator of x plus 3, one with the denominator of x minus 2. Now if you notice, my highest power here is 2, and I have two fractions here. This is a linear term, meaning if I were to graph x plus 3, it would be a straight line. Linear term, x is the highest power of 1. So my numerator would be these constants then. So if I have a linear denominator, I have a constant numerator. And then I'm ready to go ahead and solve for a and b. So this is my fraction, my partial fraction decomposition beginning. Now one more time, my highest power here is 2, and I have two constants that I'm solving for, and that should always be the case. So the easiest way to solve here is to clear the fraction, and we're going to clear the fraction by thinking about this common denominator. On the left-hand side, I'll leave that, and then on the right-hand side, my common denominator would be the product of x plus 3 times x minus 2. So again, I have this a and this b that I'm working with. And on this one, I already have an x plus 3. This one, I already have an x minus 2. So I'm going to multiply by my missing factor, which would be x minus 2 top and bottom. And over here, it would be x plus 3 top and bottom. And again, I'm just finding a common denominator. Now, once you find a common denominator, what you can do is just totally drop it. So the idea, after I have a common denominator, is I can just equate the numerator terms. So my expression is 5 equals a times x minus 2 plus b times x plus 3. So we need to solve for a and b here. Now there's several different ways that we can do this. The first one I'm going to do is I'm going to be using substitution, and I'm going to be looking at this and thinking, you know what would make this a go away? Well, what would make this a go away is if I let x equal 2. So let's let x equal 2. So I plug it in on the left. There's just a constant there, so there's no x value to plug in for. But over here, when I plug in, you'll see that a will drop. And then I'll plug in 2. So I have 5 is equal to a times 0 is 0. B times 2 plus 3 is 5b. I divide both sides through by 5, and I get that b is equal to 1. So now I know b is equal to 1. Next thing I'm going to do is I'm going to sub in, and I'm going to get rid of the b by letting x equal negative 3. And again, there's more than one way to do these. These are just usually the simplest way to get to our solution. So I plug in on the left, and again, there's no variable there, so I just have a 5. Then I have negative 3 minus 2 plus b times negative 3 plus 3. So just like I had over here, this term went to 0. This term goes to 0 as well. And I have 5 equals negative 3 minus 2 is negative 5a. Divide both sides through by negative 5. And here I get a equal negative 1. So these are the numerators. So what I've ended up with here then is my partial fraction decomposition of 5 over x squared plus x minus 6. And again, you have to be really careful about factoring these correctly. That is equal to a, and these have to go above the correct fractions. So a over x plus 3 plus b over x minus 2. So that's the correct partial fraction decomposition. Now our hope is we couldn't integrate over here before. We couldn't integrate this, but I can integrate over here. So now I'm going to take this and rewrite. And when I rewrite this expression, I should be able to integrate it now. So I'm going to have a negative 1 over x plus 3. And I'm going to go ahead and write these as separate integrals right now. I guess I don't have to. I could split them up in my next step. Now one thing you don't want to do, you don't want to look at these and think, oh, I'm going to find a common denominator and recombine these, because what will happen is you'll get back to your original expression which you couldn't integrate. So we want to leave it in this particular form. Now I'll split it up into two separate fractions, negative 1 over x plus 3 dx plus 1 over x minus 2 dx. And now both of these can be solved as a nice little 1 over u du. So for here, u is equal to x plus 3, du is dx, so I have everything I need there. So this would be a negative 1 integral 1 over u du, which integrates into natural log absolute value of u, but u in this case was x plus 3. Now let's go ahead and look at our next one. Here, u is going to equal x minus 2. du is dx. Now that's not always going to happen, that du is dx, so you always have to be careful and double check these. I don't have a coefficient to pull out here, I just have this 1, so I don't have anything out front, so I'm adding these. So this is 1 over u du, which integrates into natural log absolute value of u, and u in this case is x minus 2. So my solution then, I'm going to write my positive coefficient first, so natural log absolute value of x minus 2 minus natural log absolute value of x plus 3 plus c is my solution, or is a solution. But remember, the log, if I talk about the difference here, difference of the logs is equal to a rewrite of the quotient of the log. So this would be equal to the natural log absolute value of x minus 2 over x plus 3 plus c. And we want to simplify these as much as possible. And so this would be my correct solution. That would be how I could integrate that expression up above. So these get pretty long. There's a lot to keep track of, so you want to be really careful about organizing your work. Let's go ahead and look at quite a few more examples to give you some experience and some background on these before you start your homework sets. Now remember, we're interested in looking at factors. So we're looking at linear factors, we're looking at quadratic factors. On our next problem, we're going to have a combination of both linear and quadratic. So I'm going to have x times the quantity x squared plus 1 quantity squared dx. Now there could be something that we could do here other than partial fraction decomposition. I see a u squared plus a squared, which would be a trig sub for u equal a tan theta. I don't know how it would go. I don't know how ugly it would get, but we might try a trig sub on this if you wanted to. I'm going to go with partial fraction decomposition. Now, first thing I want to do is to check, is the degree in the numerator less than the degree in the denominator? And yes, it is. So we're good to go. We don't need to do the long polynomial division. Okay, next thing I need to do is factor completely, and it already is factored for us. That's nice. And if I look at this in terms of factoring completely, I'm going to have x squared plus 1 times x squared plus 1. So I'm just kind of writing out the factors here. So let's go ahead and look at the highest power in the denominator. So let's look at the degree in the denominator. Now this would be x to the first, and then this x squared would be squared. And I'm not worrying about any of these other constants, I'm just looking at the highest powers here. So this would be x times x to the fourth, which would be x to the fifth. So that means I'm going to have the letters A, B, C, D, and E for this problem. So I'm going to be using all of those letters because I have highest power in the denominator would be to the fifth once I combine these, and then I would have 5 constants that I would need to solve for then. So let's go ahead and start writing these out. When I write the factors out, this is a little bit tricky sometimes. I'm going to drop my integral and just work with the expression to begin with. So I have x times a quantity x squared plus 1 quantity squared. So I have factors, and I usually like to list my linear factors first. So my first linear factor would just be x, because it's x to the first power. So that's just x. I have another factor here of x squared plus 1. And I don't need to write this, but I'm going to go ahead and write this to the first power so we can see that. That is a factor here as well. Now my other factor, and this is sometimes a little bit tricky to think about, is x squared plus 1 quantity squared. So when I write all my factors, I have x squared plus 1 is another factor, and another factor is x squared plus 1 to the second power. Okay, so I have to think about all of those. Now this first one is linear, so my numerator would be a constant. My next one, this base, is quadratic, so my numerator would be linear, bx plus c. Over here my base is quadratic, so my numerator, I don't care about the squared here, I just care about the base power, would be dx plus e. So notice I use a, b, c, d, e. Here's my constants up here, a, b, c, d, e as well. So now I'm tasked with finding a, b, c, d, and e. So these can get pretty ugly sometimes, but as long as you keep track of everything, you should be fine. So what we want to do is find a common denominator. Now once we find a common denominator, then I'll worry about solving. One of the things I don't want to have to worry about though is kind of backtracking and trying to find pieces and parts I've left behind. So always be sure to drag everything along, because these problems get so long that sometimes if you don't keep everything together, you might lose something. So I need x times the quantity x squared plus 1 to the second power. So if you notice on this first one, I'm missing x squared plus 1 to the second, top and bottom. I'm trying to find that common denominator. Okay, my next one, I have a bx plus c here, and an x squared plus 1 that I already have in the denominator. So here I'm missing x times x squared plus 1 to get that common denominator. So for my next one, I have dx plus e over x squared plus 1 quantity squared. And then to get the common denominator, I'm missing an x. And so now you can see that I have a common denominator. And once I have that common denominator, you can just go ahead and drop it and equate the numerator. But you can't drop it until they're all the same. So I have a x squared plus 1 quantity squared. And I'm going to pull this x out front so I don't lose it, plus x times bx plus c times x squared plus 1 plus x times dx plus e. Now, I could think about starting to expand this, but you can see that it's going to get pretty ugly. So as I'm looking at this side, it looks like to me, if there's nothing I can plug in here, x squared plus 1, to get a 0 back out, but I could plug a 0 in here and this whole term would drop, and a 0 in here, this whole term would drop, and I should be able to solve for a then. So that's going to be my strategy. Now every time you look at a problem, it'll work a little different for each problem, but a lot of times starting with x equals 0 will make this a pretty straightforward little work. So I'd have 2 times 0 minus 1 on the left, and then over here on the right, I just go ahead and start plugging in. And as soon as I plug in 0 here, you can see all these terms just drop away. Okay, so 0 times anything is 0, 0 times anything is 0. And it looks like here then, on the left, 2 times 0 is 0 minus 1 is a negative 1. And then I'm left with 0 squared plus 1 is 1, 1 squared is 1, and I'm left with a equals negative 1. Okay, so now I need to remember that. I have a equals negative 1. So now that I know a equals negative 1, what I can do then is I can look at my expression and I can plug in for that value. So in place of this a, I'm going to have a negative 1, x squared plus 1 quantity squared. And again, there's as many ways to solve for these constants as you can imagine. I mean, there's linear algebra, there's different ways that we could substitute, we could expand these and equate the coefficients. So again, there's a lot of different ways to work this. So if you have a different method or a different approach that you'd like to take, that's great. Just make sure that you show your work. I think what I'm going to do from here is expand. Once we have because I can't plug anything in here. There's nothing I can plug in here to eliminate any of these variables. Okay, so that's why I want to go ahead and expand this. So this would be a negative 1 out front, x to the 4th plus 2x squared plus 1. And here I'll have bx squared plus cx times x squared plus 1. And then here I'll have a dx squared plus ex. So again, I'm going to distribute and expand. Don't drop the left-hand side because that's going to be really important here. So I have a negative x to the 4th minus 2x squared minus 1. Now I'm going to FOIL this first outside, insides, and lasts. Bx to the 4th plus bx squared plus cx cubed plus cx plus dx squared plus ex. Now what I'll want to do is I'll want to group these together. I want to combine as much as I can that are common. So when I do that, I'm going to be able to do something called equating the coefficients, but we're not quite ready to do it quite yet. So I have my x to the 4th terms, and so if I factor out an x to the 4th, I'll be left with b minus 1 x to the 4th. Okay, so if we want to think about it, this one's gone, this one's gone. Now I don't have any third powers, do I? Oh, I do. I have a cx cubed. Okay, so I'll include that as well. So c x cubed, and so this term is gone. And now I can worry about my squareds. I have quite a bit going on here for squareds. It looks like I have b plus d minus 2. Okay, and then next it looks like I'll have my x powers. But let's go ahead and get rid of these, my squareds. My x powers would be the cx plus ex, and what I'm doing is I'm factoring as I'm going here. So this would be c plus e x. So I'm done with this one. And then minus 1 at the end. So the method that we're going to be using now is called equate the coefficients, or equating the coefficients. Now if you notice on the right-hand side, the highest power is x to the 4th. Over here on the left-hand side, I don't have any x to the 4ths. So I'm going to call this 0x to the 4th. I don't have any x cubes either, so I'll call it 0x cubes. I don't have any x squareds either, so that would be 0x squared. However, I do have a 2x, and I do have a minus 1 for my constant. So you can see on the left-hand side, a lot of my coefficients are zeros. Now on my right-hand side, I just have the same expression. Hopefully I have enough room to fit it in here. Now the easiest thing to do when you're equating coefficients is to make sure that you start with the easiest ones. If you don't start with the easiest ones, what ends up happening is the problem gets uglier instead of better. So for instance, when I talk about the easiest ones, if I look over here on the right-hand side, the easiest one is c. I can figure out c really easily because it's just one term here to equate to my coefficient over here. So here, c would be equal to 0. So that's our first one. So right away we can let c equal 0. Another one that we could do then is b minus 1. So that would be right here, b minus 1 equals 0. I'm equating the coefficients. And b minus 1 equals 0. That would mean b is equal to 1 when we add the 1 across. So I have a from above, I have b, and I have c. And then let's see what else we can do here. Let's look at our squareds. My squareds would be b plus d minus 2 is equal to 0. But I do know what b is. So b is equal to 1. So 1 plus d minus 2 equals 0. 1 minus 2 is negative 1. Add that 1 across and I get d equal 1. So there's another solution. Okay, what haven't we used yet? So we've done, looks like our constant in front of my linear term is 2 here. Over here it's c plus e. So I have c plus e equal, not x, equal 2. But I know what c is. C is equal to 0. So I get e equal 2. Now one thing that we could do just to check here, notice that my constant on the left is equal to my constant on the right. So it looks like everything's going to work out pretty good here. So let's go ahead and recap what we have. Remember from above we found A was -1. So we have A is -1. We have B is 1. We have C is 0, which is nice because when we get something to be 0, it makes my integration a lot easier because a term drops out. And I have E is 2. So what I'm going to do is I'm going to come back up here and rewrite these coefficients in the numerator of this decomposition. So I'll have A over x. So I have the integral -1 over x dx plus, and I'm just going to split these out into separate integrals, b x plus c over x squared plus 1. So again, this was a. This is going to be bx plus c. So that's going to be 1x plus 0. And I'm just going to make sure I plug that in now with a 0, and I know I'm not going to need it later, but I want to just show that that's been done. And then I have c dx plus e is next. And that denominator was x squared plus 1 quantity squared dx. So dx would be 1x plus 2. Okay, so this is what I have to integrate now. Usually, with these linear terms, this little integral is pretty straightforward. This is of the form 1 over u du. So this integrates into minus natural log absolute value of u. U in this case was just x. And I'm going to circle this, otherwise I will lose it or forget it somewhere. Because like I said, we're doing a lot of work here. There's a lot of problems that we're working on. Okay, the next one I want to look at, I just have x over x squared plus 1 dx. Now if you wanted to look at this in terms of u squared plus a squared and do like a u equal a tan theta, you could, but go back to the original. Go back to our basic integration skills we learned, and we would look at this and think u substitution first. So think simple first, and if simple doesn't work, then you can get more complicated. Du is 2x dx, so I'd multiply by a 2 on the inside, compensate with a 1/2 on the outside, and I have 1 over u du then, which of course integrates into natural log absolute value of u. U in this case was x squared plus 1. So here's another part of my solution. Now this last one is not going to be so simple. This is going to be x plus 2 over x squared plus 1 quantity squared. Now there's one thing that I could look at here. I could look at this and think about separating the numerator. That would work. I can separate the numerator. I can never separate the denominator. So that's something to keep in mind. Another thing that might work here, this is a u squared plus a squared. So maybe a trig sub would work, u equal a tan theta. But because of this x plus 2 up here, I don't really want to go with that. If it was just an x, I might try it, but this plus 2 I think might throw a wrench and make a complication there. So what I'm going to do is rewrite this into two separate fractions. I'm going to have x over x squared plus 1 quantity squared dx plus 2 over x squared plus 1 quantity squared dx. And again, it's just a strategy to try. It's called separating the numerator. You can always separate the numerator. You can never separate the denominator. So let's go ahead and look at this first one. Let's let u equal x squared plus 1. Again, go back to the basics and see if the basics will work here. Du is 2x dx. I'd multiply by 2 on the inside, compensate with a 1/2 on the outside, and I'd end up with 1/2 integral 1 over u squared du. I'd flip that up top, and then I'd go ahead and do my add 1 divide by a sum. So I'd have u to the -1 divided by a -1. So here this would be a minus 1 over 2u, but u in this case was x squared plus 1. So there's the third part of my solution. So each of these red boxes are a part to my solution. Now it looks like so far this is working pretty slick. Now I have to look at this last one, this 2, the integral of 2x squared plus 1 quantity squared. Now if I look at this, I can think, oh, maybe I could do a partial fraction decomposition, because it's in factored form, and I could do my ax, a new ax plus b, and a new cx plus d. But I don't think I want to go that route. I think here I see this u squared plus a squared. I think a trig sub would work. So I want to look at this in terms of a trig sub. So my trig sub would be x squared plus 1 squared. So this fits the form u squared plus a squared, and the recommended substitution then is to let u equal a tan theta. So u in this case is x, a is 1 tan theta. So I'll just go ahead and rewrite that, x equal tan theta. Then I need my derivative. Derivative of tangent is secant squared theta d theta. And then I substitute in, and I'm going to run out of room here in a second. So when I substitute in, I'll pull that 2 out front. Now remember, dx needs to be subbed in for, so that's going to be secant squared theta d theta. Now my denominator, square root, no it's not square root, it's quantity squared, I better be careful there, is x squared, but x is tan theta, so this is going to look like tangent squared theta plus 1 quantity squared. So simplifying, if you recall, tangent squared plus 1 is secant squared, so this is secant squared theta quantity squared. So this is going to be secant squared theta over secant to the 4th theta d theta. And of course we have canceling occurring here, and I have 1 over secant squared. So this looks a lot better. I still can't integrate this, so I'm going to flip it up top, and actually I'm going to come over here to give myself some more room. So secant is 1 over cosine, so 1 over secant squared would be cosine squared. So this is one of my half-angle identities to integrate cosine squared. This would equal 1 plus the cosine of 2 theta all over 2 d theta. So this is back when we were learning about trig integrals. So I'm going to split this up into 2 pieces. This is going to be the integral of a half plus, better not forget my d theta here, half d theta plus integral of half cosine of 2 theta d theta. Well, the integral of half d theta, I can work with that. The integral of a half d theta, actually, you know what? I'm going to backtrack on this. I think I have, oh, I dropped my 2. See, this 2 right up here should be out front here as well. And if I do that, then these 2's cancel, and then this is a lot easier problem. And I'm all for making these a little bit easier. You can see how long these are. They're fun though. So I canceled the 2's and I separated this out into 1 d theta and the cosine of 2 theta d theta. Well, the integral of 1 d theta is just theta. And then over here, u is 2 theta, du is 2 d theta. So I'd multiply by 2 on the inside, compensate with a half on the outside, and this would be 1/2 integral of the cosine of u du, which is the integral of the sine of u, 1/2 integral sine of u, and we know u in this case is equal to 2 theta. Okay, you'd think we would be done now, but not quite. So we have theta plus 1/2 sine of 2 theta. Now something to remember here, our original was in terms of x. So I need to switch these back. So original was in x terms. So I need to switch these back, and if you remember from our trig sub, we need this triangle to help us with that. I need to make sure it's a right triangle so I can use SOHCAHTOA. And I need to mark the angle that I'm using. Now what trig sub do I come back to? I come clear up here, back to my original substitution, x equal tan theta. So I have x equal tan theta. So tan theta equal x over 1. Tangent is opposite over adjacent. So from this theta, opposite would be x, adjacent would be 1. The hypotenuse using Pythagorean's theorem would be the square root of x squared plus 1 then. Okay, so what's theta? Well, I can find theta pretty easily from right here. From here, theta would be the inverse tangent of x then. So that could start here, the inverse tangent of x. And then what I could do for my next one is this half. This is a problem. I don't know what 2 theta is. I only know what theta is. So I'm going to have to apply a double angle identity here. The sine of 2 theta, this is a common one that we've used before, is 2 sine theta cosine theta. Now everything is in terms of theta, so this will be easier for me to work with. The half times 2 cancel, so I don't have to put that in. And then the sine of theta, remember sine is opposite over hypotenuse. And then I have cosine of theta as well, which is adjacent over hypotenuse. So this is equal to the inverse tangent of x plus x over the root x squared plus 1 times root x squared 1 is just x squared plus 1. So this is another 2 parts to my solution. Now, I can't remember all of our parts. So if we come back up here, everything I have boxed in red, I have minus ln of x plus half ln of x squared plus 1. So I'm going to combine my solutions. I already forgot what it was. So minus ln of x absolute value of x. And then I also had plus a half ln of x squared plus 1. My third piece up here was minus 1 over 2 x squared plus 1. And this is 2 times the quantity x squared plus 1. And then I finally have these last 2 pieces that I just finished. Plus inverse tangent of x plus x over x squared plus 1. Now I have a plus c for my constant of integration at some point, but I think I can do some simplifications here. X squared plus 1 is always positive, so I could rewrite this as popping this half up front, remember, would give it a half of my exponent. So this would be the ln of the square root of x squared plus 1. And this would be the minus ln absolute value of x then. Now remember, these can combine. If I look at the difference of the logs, which this is, that's equal to the log of the quotient. So this would be log square root of x squared plus 1 over the absolute value of x, so I could combine those. This inverse tangent, obviously there's nothing to combine there because there's no other inverse trig functions. And this x squared plus 1, I think I could work with this, get a common denominator, multiply top and bottom by 2, and combine those, and then this would look like 2x minus 1 all over 2 times the quantity x squared plus 1, and then plus c, my constant of integration. So this is as simplified as it gets. Now definitely an indefinite integral. I'm not evaluating this, so I need my plus c. You could potentially evaluate these, but we can worry about plugging in your upper and lower in your homework sets and not in the lectures, because you can see how long these problems are. So on this problem, we were solving for 5 factors, and then we had to integrate. And each one of those different integrals used a different integration technique that we've used from Calc 1 and learned recently in Calc 2. Now this lecture gets pretty long because one problem I think took us about 20 minutes, 25 minutes. So let's go ahead and do a couple more problems. And again, you can zoom through parts of these if you understand the integration technique, or if you just need help with the partial fraction component, that's good as well. So our hope is as many coefficients as possible will eventually go to 0, which makes our integration easier. Let's look at x cubed. I'm going to see if I can find a different pin here. Let's go ahead and look at the integral of x cubed times x squared plus 7 dx. And the numerator will have a 7x squared. Now a couple things going on here. First of all, if you look at the x squared, it could cancel into the x cubed, and so I could simplify this expression first if I wanted to. I'm going to show you what will happen if we do that. Nothing bad will happen, but I just want to give you a heads up about what will happen. So first thing to check, is the degree in the numerator less than the degree in the denominator? And yes, it is. Next, is it factored completely? And yes, it is. Okay, next thing we want to look at is we want to talk about the degree in the denominator. So that's going to be x cubed times x squared. Basically, there's going to be other factors, but the highest powers are what I want to look at. So this is x to the 5th. So that means I'm going to have an a, b, c, d, and e. I'm going to have 5 of those coefficients. So again, we could cancel here. I want to write it out and show you what will happen if you don't notice that and don't cancel. So rewriting my partial fraction, I'm going to have 5 of these. 5 a, b, c, d, e. That doesn't mean I have 5 fractions, though. It just means I have 5 of these constants that I'm solving for. So if I look at x cubed, x is definitely a factor there. Another factor of x cubed is x squared, and another factor of x cubed is x cubed itself. And that leaves me with x squared plus 7. So when I think about my x, a factor of x cubed is x, another factor of x cubed is x squared, and another factor is x to the 3rd. Now some people have a little bit of trouble with this because they're saying, oh no, x squared is not a factor. Well, let's think about 8. The factors of 8 are 2, 4, and 8. Well, 8 is 2 cubed, so this is 2 to the 1st, 2 to the 2nd, and 2 cubed. So if you want to think about it as a constant in there, it might make it a little bit easier to work with. Now when I look at my coefficients, this is linear, the base is linear, so my numerator is constant. The base, I don't care about the exponent here, I just care about the base, is linear, so my numerator is constant. The base is constant, I don't care about the exponent here, so my numerator is linear. Now here my base is quadratic. If you want to think about this, my exponent is to the 1st power, so my numerator is going to be linear, dx plus e. So I have this set up and ready to go, and I'm going to find a common denominator. So as I'm working on this denominator, I really think a lot of things will go to 0, and that's because I didn't cancel here. So I have an a over x, then I'll worry about what's missing. I have a b over x squared, and I'll worry about what's missing. I have a c over x cubed, then I have a dx plus e over x squared plus 7. And then I'm going to go through and just find that common denominator. So here I'm missing an x squared times x plus 7, top and bottom. Here I'm missing an x times x plus x squared plus 7. Here I'm missing an x squared plus 7, top and bottom. And this last one I'm missing an x cubed, top and bottom. So once I find that common denominator, I can drop it and just work with the numerator. So I have 7x squared equals, and I'm not going to expand anything right now, because I think I can eliminate a lot of these variables by choosing x equals 0 to start with, but we'll see what happens. I'm going to pull this x cubed out front here. Okay, so if I let x equals 0, on the left-hand side I have 7 times 0 squared. And on the right-hand side I have a 0 squared times 0 plus 7 plus b times 0 squared plus 7, c 0 squared plus 7, 0 cubed d times 0 plus e. So what will go to 0 here is this term goes to 0. Now be careful, this term doesn't. This last one does though. 0 squared plus 7 is 7. So I end up with 0 equal 7c. If I solve for c, I get c is equal to 0. So there is one of my coefficients. Now if c is equal to 0, I can come back up here and rewrite, and then try and solve for my other variables. So when I rewrite, I get 7x squared, and I'm going to expand this now. I get ax cubed plus 7ax squared plus bx cubed plus 7bx. Now c was 0, so this whole term will go away. And then I have dx to the fourth plus ex cubed. Now I will group my coefficients. So I have my cubes. Whoops, I have a fourth power. So I have a d x to the fourth. And then my cube would be a plus b plus e x to the third. I have to kind of keep track here. So I'm done with this one. I've got a cube, x to the fourth. I'm done with that one. My next one would be a second power. So it looks like a 7a x squared. And then my constant, oh wait, I have a linear coefficient here of a 7bx. And then I do not have a constant. So when I equate my coefficients, if you notice I don't have an x to the fourth over here, so d would equal 0 right away, because there's no 0, or there's a 0x to the fourth over here. Now over here I have a plus b plus e would equal 0, because there's no x cubed over here on this side. 7a is equal to 7, because I have a coefficient of 7 over here. And then 7b is equal to 0, because I don't have a linear, just an x term over here. So solving, it looks like b equals 0. So there's a nice solution. And again, the more things that are zeros, the better. Here, a is equal to 1. And now once I know these two, I can substitute in here. A is 1, b is 0. And then if I subtract the 1 across, I get e equal negative 1. So there's another solution here. And then of course d equals 0. So let's regroup here. I have a is 1, b is 0. Oh, I got 3 of them to go to 0. We might actually be able to integrate this one pretty fast. So a is 1, b is 0, c is 0, d is 0, and e is negative 1. So what I'll do is I'll come back and I'll plug these back in to my original fraction decomposition. So I have a over x, which is really easy to integrate, so that makes me happy, plus b over x squared plus c over x cubed. Now my last one was dx, so 0x minus 1 all over x squared plus 1. No, it's not x squared plus 1. Is it? X squared plus 7 dx. Now if you notice, I'm just writing these out. I know that these are equal to 0. C was 0, so I can just plug a 0 in there. Notice this term, the second and third term here, goes away. Well, what happened then, remember at the beginning I said we could have canceled the x squared into the x cubed and just gotten x? That's exactly what happened here. Is the partial fraction decomposition kind of fleshed that out and dropped those terms I forgot to factor out. So if you could have canceled at the beginning, this would have been a lot easier. Now, integrating this, the integral of 1 over x dx is equal to the natural log absolute value of x. And then this piece over here, I'm just going to pull that minus 1 out front. This is x squared plus 7. But 7 is the square root of 7 quantity squared dx. And this fits a form. This fits the form u squared plus a squared, where u is equal to x and a is equal to the square root of 7. So this recommended substitution is to let u equal a tan theta. So I'm using trig sub here. Love the trig sub. So my substitution would be x equal root 7 tan theta. Dx would be root 7. The derivative of tangent is secant squared theta d theta. And then I start plugging in. Now don't forget there's a negative sign out front. I'm going to come over here to give myself more room to work. Now dx is root 7 secant squared theta d theta. And in my denominator would be x squared, which would be root 7. You know what? We can keep this process up and we're going to be just fine. We'll get our solution, but I see a shortcut here. So I'm going to not use trig sub on this. We could and we'll get an answer, but I see a shortcut because remember we memorized some forms. And if we can spot those forms, it'll save us a lot of time and potentially mistakes. So this fits a form, and so I want to go after that form. Now that form that it fits was 1 over u squared plus a squared du, which is 1 over a inverse tangent u over a plus c. So this fits it perfect. So no need to go through trig sub. We'll get the same answer in the end, but this is a lot easier if I can recognize that form. So u is equal to x, a is equal to square root of 7, du is dx, so I have all of those pieces here. So this integrates into 1 over the square root of 7 inverse tangent of u, which is x over square root of 7. So these are my two pieces. Now I think I forgot though that we have a negative 1 right here. So I want to make sure that it gets included down here. So my final answer then would be natural log absolute value of x minus 1 over root 7, which you can rationalize if you'd like to, inverse tangent x over root 7 plus c, my constant of integration. Now there's really nothing I can combine there, but like I said, you could, if you wanted to, go ahead and rationalize those denominators, but it's not necessary. Now some problems have repeated linear factors that are a little bit difficult to see, and we'll also see on this problem the advantage of simplifying an expression if you can before you get started. So if we look at this integrand, we'll notice that the x squared could cancel with the x cubed, and I could rewrite this, and we could integrate this using partial fractions. It looks like we might be able to use a little I think that we could also use maybe some inverse tangent here. We'll have to check it out for some trig sub. But I want to use partial fractions on this to show you how to use repeated linear factors. So to get started, the first couple things that we want to check out are, is it degree in the numerator less than the degree in the denominator? And yes, that's true. Is it factored completely? And it is factored completely. It's not simplified completely for this case, but usually I'd probably want to cancel here. I just want you to see the effect if you don't do that. And then we want to check out the degree in the denominator. The degree in the denominator, if I look at the highest power, would be x cubed times x squared. I don't care about all the other powers, I just want the highest powers. So this leaves me with x to the 5th. So that tells me I'm going to have 5 constants a, b, c, d, e that I'm going to have to solve for. Okay, so let's go ahead and rewrite this. Now when you have these repeated linear factors, sometimes you look at them and you think, oh, this is a quadratic term or this is a third degree polynomial. It is, but we want to think about this in terms of factors. Okay, so if I think about the factors of x cubed, let's kind of do this off to the side here. So factors of x cubed, x is a factor, x squared is a factor, and another factor is x cubed. Now if you don't see those three factors, another way to think about this is think about the number 8. The factors of 8 are 2, 4, and 8. But 8 is 2 cubed, so that's 2 to the 4th, 2 squared, 2 cubed. So these are those factors. So let's go ahead and write these as x, x squared, x cubed, and then this last one, this quadratic factors, as x squared plus 7. Now if you look at the base, just the base here, not the exponent, that's an implied 1, it is linear. It's x to the 1st. So my numerator has to be constant. If we look at just the base here, the base is linear, so my numerator is constant. If I look at just the base here, the base is linear, so my numerator is constant. And here my base, x squared plus 7, if you want to think about that, it's to the 1st power, is quadratic, so my numerator is linear, so that would be dx plus e. So this is my partial fraction set up. And then once I have that set up, I find a common denominator. So find a common denominator. And then once you find a common denominator, we just drop it. Now if you want to think about it as multiplying through to clear the denominator, you can, but I just like to kind of think about it as dropping them. So again, I'm going to set this up so it's easy to find that common denominator, and then just get rid of it. Okay, this is missing x squared times x squared plus 7. And again, I'm looking at what I need to get that common denominator of x cubed times x squared plus 7. This would be x times x squared plus 7. This already has the x cubed, so I just need the x squared plus 7. And this one is just missing the x. Now I have that common denominator, and now I just drop it. So looking at the numerators, I have ax to the 4th plus 7ax squared plus bx cubed plus 7bx plus cx squared plus 7c plus dx squared plus ex. Okay, now as I'm looking through here, I see that I should have an x cubed, so this should be a cubed right here. So this should be dx times x cubed would be dx to the 4th plus ex to the 3rd. I think that looks better. Now as we're working through this, I could have let I could have let x equals 0 and solve for c, but I'm just going to go ahead and equate coefficients on this one. So I'll group my like terms. So I have an ax to the 4th and a dx to the 4th, so that would be a plus d x to the 4th. So that one's been used. My next one is cubed. So this would be b plus e, because I'm factoring out that coefficient x to the 3rd. Now I'm looking for squareds. So I have 7a plus c x squared. Now I'm looking for my linear terms, which would just be the x terms, so that would be 7b is my coefficient. My variable is x. And then over here my constant is 7c. So now let's go ahead and set these up and equate. So a plus d would equal 0. The reason why it's 0 is there's no x to the 4th over here on this side. So there's 0x to the 4th. So that's why I equate that coefficient. This one is b plus e equals 0 because there's no x cubed over here. 7a plus c, however, would equal 7 because over here the coefficient in front of the x squared is 7. 7b would equal to 0 because there's no x's on this side. And over here 7c would equal 0 because there's no constant. So going through and solving, I get c equals 0. Here I get b equals 0, and the more things I get to equal 0, the better. And then plugging in over here, if c is 0, I have 7a plus 0 equals 7. So if I divide through by 7, I get a equal 1. And then over here, I already know b is equal to 0, so I have 0 plus e equal e. So this means e equals 0. So there's another one. I'm happy with all these zeros. Now over here, a plus d equals 0. I know a is 1. 1 plus d equals 0, so d would equal -1 when I solve. So these are my constants. Now again, I could have substituted in x equals 0 and then done this. I just chose to do it right off the bat because I knew I wasn't going to be able to get rid of very many. So let's see the effect here. So a was 1 over x dx plus b was over x squared plus c was over x cubed plus e was 0x minus d over x squared plus 7 dx. whoops, I have that backward. So dx would be a negative x plus e. In this case, e was 0. So again, this was a, b, c, d, e. Now look what happened with these zeros. The b and the c went to 0 because if you look back to your original, these would have canceled. I would have had just 7 over x. So the x squared and x cubed terms go away. So even if you don't get that cancellation, that'll drop out. It just makes a lot more work if you don't notice it right away. So we could have simplified at the beginning. So let's go ahead and integrate what we have. 1 over x dx. I'm going to pull the negative sign out front over x squared plus 7 dx. This is natural log absolute value of x. Now this one, we're going to use a u substitution. Remember, go back to the original integration techniques we knew. Straightforward u substitution. So u is equal to x squared plus 7. du is 2x dx. Now I have the x, but I don't have the 2. So I'll multiply by a 2 on the inside, compensate with a 1/2 on the outside. And I have minus 1/2 integral 1 over u du. So continuing to simplify, I have natural log absolute value of x minus 1/2 natural log absolute value of u, but u in this case was x squared plus 7. Now the log, the difference that we see here, right here, the difference of the logs, I can rewrite as the log of the quotients. So this would be the natural log absolute value of x over the square root of x squared plus 7. Plus c. Now the square root comes in because I can take this half and I can pop it up top. So this would be my solution. Now again, it's natural log of x divided by the square root of x squared plus 7. Now these problems get pretty long and we have to employ a lot of different integration techniques for many different sections, but the key to it is clean, neat, orderly work. So you can go back and find any mistakes if you have any, or you can also section them off, because like on some of these parts when I was doing a lot of different integrals, maybe writing each one separately and working them and then bringing them together at the end. When you're working these problems, be careful with your algebra. It's a lot of room to make mistakes. I often drop a sign or forget a negative and I always have to go back and double check. So be real careful, make sure you show all your work with these, and again, if you have questions, please send me a screenshot. I'm happy to help. You also have your option for Pearson Connect to a tutor, and also online office hours if you would like to set up an appointment as well. Good luck, and I hope you enjoy working on these.